So the nice thing working with algebraic vectors, which are positioned on an xy in 2 dimension or an xyz plane in 3 dimensions, is that now we can handle them with numbers. Instead of being a geometric vector, which is a line drawn on a page somewhere with a given length and direction that we can float around and move as needed, it's a little bit more comforting when we work with numbers. But what we need to get used to is sketching in 3 dimensions. So for question number 1, we're going to sketch and find the magnitude of 2 vectors. The first one is given to us in point or coordinate notation, and then the second one is given to us in unit vector notation. So sketching in 3 dimensions can be a little bit tricky. I start by giving myself what looks like a normal axis, but then the third axis is the one that comes out of the page. So then I draw a line going like that. Now, X is the one that comes out of the page. Y is the one that goes side to side, because they really took the XY plane that we're used to and flipped it. So now that it's coming out, and Z is the one that goes up. So now I'm going to take each of these numbers separately and replicate the movement on here. So positive 5 on the X is negative going back or positive coming forward. So I'm going to move to about where positive 5 would be. From that point, I'm going to go positive 4 on the Y. If it was negative at this point, I'd move back, but because it's positive, I'm going to line up to where about positive 4 would be on the Y. So now I'm lying on this plane and Z goes up or down. Because this is a negative, I'm going to go down 2 from that point. So it's hard because negative 2 is actually there, so it's about there because it's really underneath this point. And it is hard to get the 3 dimension. But you go forward 5 over 4 down 2 to get a better indication of what it would look like. Now, unit vector notation is the exact same. I just represents the unit vector in the direction of X. J represents the unit vector in the direction of Y. And K represents the unit vector in the direction of Z. So I'm going to give myself my axes. X, Y, Z. So J would be a little unit vector there. Sorry, I would be on X, J would be on Y, and K would be on Z. But it really just works the same way. I'm going to go back 2 on the X, forward 4 on the Y, and then down 2 on the Z, and from the origin to that point represents my vectors. Now I'm going to go back and find the magnitude. Well, the nice thing is Pythagorean theorem does kind of extend to 3 dimensions. You make all sorts of triangles and move around until you get to your ultimate length. If you Google it, you'll see a proof of why it works. But I can really just do, okay, in this case, the magnitude of U is going to be 25 plus 16 plus 4, which is going to be root 45. Or 3 root 5. Because don't forget, we're used to working with radicals, and root 45 is 9 times 5. The root of 9 is 3, and 5 is left underneath. But I just square the X, square the Y, square the Z, add them together, and then square root them. So here, the magnitude of OP is going to be the root of 4 plus 16 plus 4, which is root 24, or 2 root 6, because 24 is 4 times 6. So when I reduce it, the root of 4 is 2, and I'm left with the root 6. So magnitude in sketching in 3 dimensions is not that big a deal if you remember where the actual axes are. Direction becomes a little bit different, though, because instead of being able to quote one direction to the x-axis, because now it's in 3-dimensional space, we cannot signify the direction with one single angle. So instead, we're going to look at the angle to the x-axis, the angle to the y-axis, and the angle to the z-axis. But we have formulas for that. So I have my vector u. When working with direction cosines, the first thing I need is the magnitude of u. So the magnitude of u is going to be 1 plus 16 plus 49, which is the square root of 66. I don't think that's reducible. I'm going to check it quickly with 4. Nope. So that's going to stay that in lowest terms. So our formula says the cosine of alpha is the x-coordinate over the magnitude. The cosine of beta is the y-coordinate over the magnitude. And the cosine of gamma is the z-coordinate over the magnitude. So find the direction cosines. There are the direction cosines. Cosines represent ratios or fractions. Now to do the angles, I'm just going to shift cos all of these. So shift cos -1 divided by the square root of 66 is 97 degrees. For beta, I'm going to do shift cos of 4 divided by root 66, and I get 61 degrees. And for gamma, I'm going to shift cos -7 divided by root 66, and I get 150 degrees. Now, it's difficult because people want to look for a relationship within the angles, and there's really no relationship within the angles themselves. They don't add to 180. They don't have to make up a certain thing. However, there is a relationship between the cosines, and that relationship is if we square them and add them, we get 1. So to verify that, I'm going to start with the formula cos squared gamma plus cos squared beta. Sorry, that's cos squared alpha plus cos squared beta plus cos squared gamma. And now I'm going to fill them in. So cos of alpha is -1 over root 66, and then I'm going to square it because of the 2 in the formula. Cos of beta is 4 over root 66, and then I'm going to square it. Cos of gamma is -7 over root 66, and then I'm going to square it. So then I get 1 over root 66, because root 66 squared gets rid of the root, plus 16 over 66, plus 49 over 66, and if you add that, you get 66 over 66, which equals 1, so we have verified. So that relationship is true. If you square the cosines and add them together, you'll always get 1. Don't look for a relationship in between the angles themselves.